Next, I'm going to talk about another aspect of galaxies, which are globular clusters. And so globular clusters you might know to be these clusters of relatively compact clusters of stars that are anywhere from tens of thousands to hundreds of thousands to a few million stars. And there are lots of examples of beautiful globular clusters that have been observed by Hubble. You can view them in small telescopes. And what's great is that we find globular clusters not only in our galaxy, but in other galaxies. M31 is the Andromeda galaxy, the nearest big galaxy to us. And so we've observed globulars around them, as well as around more distant galaxies. This is one observed about 25 years ago from Hubble. And each of these dots is not a star, but they're actually globulars. So we're able to find globular clusters around other galaxies. And if we look at a simulation of what our galaxy looks like, this is just a visualization. So we have about 150 known globulars, and they are all orbiting and clustered in such a way that they orbit around the center of our own Milky Way galaxy. And so you can just get a sense of them in orbit in three-dimensional space in this animation. And so the question is, where did these globular clusters come from? And that's been a big mystery because we know that the stars in these globulars tend to be relatively old. There's not very much gas to allow for star formation. And in this scenario, and we know that the Milky Way has gone through a bunch of mergers over the course of its history. So where in this merger process did these globulars come from? And it's not entirely clear because globulars are relatively small, and the galaxies that we can observe in the distant universe that basically give us a proxy of what happened to our own galaxy, those are relatively large and relatively bright, and so we don't quite see the precursors to globular clusters, at least not until recently. And this brings me to this whole idea of this galaxy zoo. And I'm not a galaxy astronomer. This is not something that I studied. But if you start looking at the literature, it turns out that there's a huge range of different names and acronyms that extragalactic astronomers who study other galaxies have come up with. So some of these might be familiar, like spiral galaxies, elliptical galaxies, dwarf galaxies, early type galaxies. But then you get lots of different types of ellipticals and different types of dwarf galaxies. And then you get these really weird acronyms, faint low surface brightness galaxies, blue compact galaxies, luminous red galaxies. And I'm sure people who do this for a living just love all the different acronyms. And then even for active galaxies, there's dozens of different types of active galaxies that people have talked about. But the reason why I bring this up is that in recent years there have been really interesting subclasses of these galaxies, and one of them are the green pea galaxies, which have again only been recently discovered in the last few years. And they're so-called named because when you look at them in red, green, and blue colors, they tend to be predominantly green, and they're relatively close by, and they do seem to be analogs of more distant types of galaxies that we have better understandings of, and they're unlike ellipticals or spiral galaxies. So here's one type, this green pea galaxy, and then continuing along this food theme, there's also the blueberry galaxies that have recently been discovered. This is from a paper from last year. And they're, again, relatively nearby, and they appear very blue, which means that they have really young, massive stars, which tend to look very blue. And so what's crazy about these galaxies is that not only are they really small, they're typically on the order about 10,000 times smaller than our own Milky Way, which means, I'm getting ahead of myself. So the blueberry galaxies are nearby, low mass, but they're forming lots of stars, which is why they're blue. But the next thing I'm going to talk about is the little blue dots, or LBDs. And so this is a paper that just came out actually last month in December. So we're getting away from the blue theme, but there's still these little tiny galaxies. And here are a couple examples of them where they had to really co-add images from them to even get good signal to noise. But okay, so these are the ones that are much smaller than the Milky Way, so about 10,000 times smaller, and that means they're typically 10 million solar masses, whereas our Milky Way is 100 billion solar masses. But what's amazing is that they're forming stars about 10,000 times faster. So in our Milky Way, we might form a handful of solar masses worth of stars per year. Well, this is 10,000 times, on the order of several tens of thousands of solar masses worth of stars. And they're forming stars so quickly that if they had a constant star formation rate, and because they're so small, you wouldn't expect them to exist more than a few 100 million years, which is really, relatively recent for galaxies in our universe, which is more than 13.5 billion years old. But what's also really interesting is that we do find they found evidence for them much further out. And if you let them evolve to today, given the size that they detect, you'd find them to result in galaxies roughly about 100,000 to a million solar masses in size, which is exactly the size that you'd expect for globular clusters. So this might be the actual precursor to the globular clusters that people have long wondered about. How did we ever get globular clusters? Well, this is one possibility.